So, now you have formed oxide, oxide from the sulphide, oxide from the carbonate, oxide from the nitrate, oxide from the sulphate, from everything you have got oxide. So, next problem is how to convert this oxide into metal. It requires heating of this oxide with some reducing agent, right. So, there are some questions how to reduce, how to choose reducing agent. Generally carbon or carbon monoxide can be a reducing agent, or another metal can also be used. Basically the purpose of the reducing agent is shown in equation by taking the example of carbon. It takes away oxygen part associated with the metal and carbon monoxide is released and metal is obtained or from the oxide, or oxide is converted into metal. So, obvious question is that is carbon suitable for all reduction? Answer is no. So, what should be the reducing agent which is suitable for a particular oxide? Now, thermodynamics is helpful in providing answer to this question. In reduction of metal, what we essentially want? Take this example, zinc oxide. We want to convert zinc oxide into zinc plus oxygen. This is in principle we want. This oxygen may be taken away by a reducing agent. Now, as such, if you heat oxide, the formation of metal is an endothermic process, and if you look at this reaction, its entropy, change in entropy is positive. Why? Zinc oxide is solid, zinc is solid, but oxygen is produced, and as a result the randomness of the system is increasing. So, delta S is positive. What is reverse? Its reverse is formation of oxide. It is written here zinc plus half oxygen zinc oxide. Now, here what is happening? It is a highly exothermic reaction, because you know all burning is a exothermic reaction. This highly exothermic reaction, for this delta S is negative because randomness is decreased. Here there was a gas, here on the right side there is no gas. So, randomness is basically decreased, right. So, delta S is negative. Now, you can visualize that if we have such two equations which gives you, which is exothermic in nature, which gives you delta S negative, and there is another equation where which is endothermic, delta S is positive, we can combine them together to give an overall reaction which ultimately gives you the negative value of the free energy, because we know that delta G is equal to delta H minus T into delta S. This is called Gibbs free energy at any specified temperature of T. Now, this Gibbs free energy for a spontaneous process has to be negative. How it can be negative? For a reaction alone, it is easy for an exothermic reaction to make this negative, because delta H will become negative, or if you have delta S positive, and in that case also this factor, the second factor is negative. It will be very easy for an exothermic reaction to make the overall delta G negative, but for an endothermic reaction you will have to increase temperature, so that the second factor overcomes the first factor and overall the delta G becomes negative. But if the delta G is not negative, then the process cannot be spontaneous and reaction cannot go. This delta G is also represented by this equation R T ln K, where K is equilibrium constant, of the reaction for which we are writing the value of delta G. So, delta G is negative if for an endothermic reaction delta H is positive and it has to be less than minus T into delta S, okay, or it can be negative when K has a positive value from the second equation. So, what we will have to do? To meet this condition, we will have to increase T, ultimately delta G becomes negative. So, this is a difficult task. You may have to increase delta G too much and the situation can become impractical. So, what is needed? That we combine another reaction with it, right, so that net delta G becomes negative and overall reaction will occur. So, this is the key to select the reducing agent, because the reducing agent is the one which has negative delta G, either because it is exothermic in nature or it is exothermic in nature plus the delta S is positive, either of the two or both of them together. Then what will happen? The overall reaction will occur, and for overall reaction the delta G will become negative. So, in the reduction of metal oxide we coupled two reactions so that sum of their delta G is negative, and not merely negative, but negative of sufficient magnitude or high magnitude. Let us illustrate this point with some examples. Suppose MXO is an oxide, we want to convert into M solid or liquid or oxygen, that is we want to reduce it. So, we want to remove oxygen from it. M star is another metal which can take this oxygen and is converted into oxide. So, delta S for first is positive, randomness increases, one of the product is gas. Delta S for second is negative. Now, if you take a real example, carbon converted into carbon monoxide, for this delta S is positive, because here 1 mole of carbon monoxide is produced from half a mole of oxygen. So, randomness is increasing. For second, delta S is negative. Why it is negative? Because you have 1.5 moles of gas which is converted into 1 mole. So, randomness is decreasing. Now, what happens? This is also a exothermic reaction, this is also an exothermic reaction, both are exothermic reactions. So, both have delta H negative. In this case delta S is negative, but this burning is also exothermic reaction. So, the together or the joint effect of change in delta S and delta H should be of the type that delta G for this particular reaction becomes negative and of high magnitude. Then that will be a suitable reducing agent. So, it can be metal, it can be carbon, it can be carbon monoxide, but the criteria is that the delta G of the two reactions, one where which we want to in which we want to convert oxide into metal, and the another one where we want to take this oxygen, the combination of the two should give delta G negative of high value. That is very important. So, this is what basically delta S, you cannot make the temperature of endothermic reaction too high. So, its contribution with any of these reactions can make overall delta G negative. So, C may be suitable, carbon may be suitable, metal may be suitable for reduction. Now, this whole thing we represent in the form of a diagram called Ellingham diagram. What is Ellingham diagram? If you write this equation, then the plot of delta G versus T will be a straight line, and this delta S will be the slope and delta H will be the intercept. Now, the plot between delta G and T is called Ellingham plot, and using this plot we can easily find out or we can easily speculate whether a particular reducing agent will be suitable for reduction of a particular metal. Here the Ellingham plot is shown. On the y axis delta G is there, Gibbs free energy. On the x axis temperature is there. Now, you look this reaction, that is Zn I write separately, for this reaction delta S is negative. Why delta S is negative? Because randomness is decreasing, a solid, a gas and a solid. So, randomness is increasing. Okay. So, delta S is negative. So, this factor has become positive. Once this factor has become positive and you know that this is an exothermic reaction, this is an exothermic reaction. So, basically the delta G at a lower temperature, as the temperature will increase, okay, this factor, this positive factor will increase. So, this will go on compensating this minus delta H and go on reducing delta G. So, at this temperature, say for example at 600 degree centigrade, as you increase the temperature, what happens? Temperature increases, but delta S is negative. So, this factor becomes positive, this factor becomes go on positive and will eat away the negative value of delta G or will reduce the net effect of these two parameters, making delta G to increase. Please note that on this the delta G is decreasing downwards, is becoming more and more negative downwards, it is becoming more and more positive upwards. So, delta G will become less negative. Now, you may ask a question that why at this point there is a change in the slope. This change in the slope may be because at this temperature the zinc oxide which is formed has changed its phase, and as a result it has changed its phase. This means delta S has become more negative, delta S has become more negative. So, this factor T into delta S is neutralizing in this exothermic reaction and decreasing delta G more. Okay. If at this point suppose the zinc oxide melts, what will happen? Delta S will suddenly become positive, and because randomness will increase, liquids have more randomness, and as a result this line will go downwards. Here plots are shown for several metals: aluminum, magnesium, iron, copper, but I will draw your attention to this plot of carbon, oxygen, carbon reacting with oxygen giving carbon dioxide. This is parallel to the x axis. Why it is parallel to the x axis? You look at it, carbon is a solid, oxygen is a gas, there is a 1 mole of gas used giving 1 mole of gaseous products. So, what was the randomness with the reactants? The same randomness has remained or sustained with the products. So, delta S is 0. If in this equation delta S becomes 0, what will happen? Delta G will be proportional to delta H, and delta H is a constant quantity. So, the curve will be parallel to the x axis. Now, look at this. Here carbon is converted into carbon monoxide. Situation is different. Here for formation of carbon monoxide from carbon, delta S is positive. This is solid, 1 mole is converted into 2 moles of carbon monoxide. So, randomness is increasing and delta S is positive. In this equation, if delta S is positive, then this factor becomes negative and delta H is exothermic, this is an exothermic reaction, to delta H is negative. The combined effect of the two, as the temperature increases, delta G will become more and more negative. So, these Ellingham plots are used to predict the appropriate reducing agent, and how they can be used to predict the appropriate reducing agent. The curve of the reducing agent should be below the metal the curve of the metal. Say for example, aluminum is converted to aluminum oxide, its plot is this. Magnesium is converted into magnesium oxide, its plot is this. The plot of magnesium, oxidation of magnesium is below the plot of aluminum. So, and this is only at a point below A. Note that below A, after the point A they are exchanging their positions. So, if you are working at a temperature below A, then magnesium can convert aluminum into aluminum oxide. Please note that these plots are always for oxidation. It is not that one plot is for oxidation and another is for reduction. No, it is always every plot is for oxidation. So, Ellingham plots are basically for oxidation and they represent the relation between delta G and the temperature. But really theoretically it is predicted from this Ellingham plot that magnesium is a suitable reducing agent for aluminum, but we do not use in practice the magnesium as a reducing agent for aluminum. There are practical reasons for it, okay, which we will discuss later, but this you can easily predict that which can be possible reducing agent. It may be used or it may not be used. That is another question or another issue. So, let me point out in nutshell that Ellingham plots only indicate the possibility of the reaction. It does not tell how fast the reduction will be if it is thermodynamically feasible. Second is that this plot is based on the assumption that there is a equilibrium between reactants and the products. Okay. This may not be always true because reactant and products may be solid. Okay. So, Ellingham plot can be a guideline, this plot can be a guideline. Apart from this, the experience and other technical parameters or technical feasibility is also considered for using a or for choosing a reducing agent. Now, let us take some examples. Extraction of iron. Iron is largely present in form of sulphide ore. So, what we will have to do? We will have to convert sulphide ore definitely via a process of roasting into oxides. Now, this oxide can be converted or reduced with carbon easily. This can be seen from this Ellingham plot. This can be easily seen from this Ellingham plot. Look at Fe plus O2 plot, it is here. Where is carbon plot? Carbon plot after at a temperature above 800 degree centigrade, both this as well as this, they are below this plot. Okay. But as the temperature increases, right, this gap between these two plots goes on increasing. This gap between these two plots goes on increasing. So, if you want to reduce iron, carbon is a suitable reducing agent, but this you cannot do at a temperature of say 200 degree centigrade. You have to raise the temperature so that overall delta G is negative. So, the reactions which occur are can be written like this. This is the two separated equations you can write, and this is a combined equation you can write. So, this is representing the two equations separately, that oxygen is taken away by this reducing agent. Now, how we do it? This reduction we cannot do it, mind it, you have to have a 173 Kelvin temperature above it. So, you cannot have it in a normal apparatus, you require a very specific apparatus for this purpose, and this specific apparatus is called blast furnace, because anything which has high temperature we call it as a furnace or oven. So, this is also having a high temperature, we call it as a blast furnace. This is shown in this figure, blast furnace. It has several parts. From the top, ore, limestone and coke. We have decided on the basis of Ellingham plots that carbon is a very suitable reagent for it. So, we add the mixture of ore, limestone and oxide. You will know the why we have added limestone very shortly, but this mixture is added. It has basically air or oxygen is blasted from the bottom. This coke which is coming, this is hot air, this will burn. So, there will be a temperature gradient in this blast furnace. The maximum temperature will be at the bottom, and here the temperature will be around 1070 Kelvin. Several reactions occur in this blast furnace. Now, when air is going, coke or carbon is coming, it will not remain in the form of carbon, it will be converted into carbon monoxide, right, because the supply of oxygen is not enough to convert directly into carbon dioxide, which we do not want, because carbon dioxide will not be able to act a reducing agent. Okay. So, we want to limit it supply of oxygen and convert carbon into carbon monoxide stage. So, iron ore is coming, it is in the form of oxide, you know that we have converted into oxide, it is coming into is this converting into magnetite with reduced. Why this process is reduction? If you look at Fe2O3 and Fe3O4, you can see the formal oxidation state of iron in this is lesser than this. Here iron is, all iron is in 3 oxidation state, here iron is 2 plus 3 both oxidation state. So, iron is in magnetite is partially reduced. This magnetite is further reduced to iron 2 oxide. In FeO, oxidation state of iron is 2. Now, this calcium carbonate or limestone which you have added, okay, at this temperature it will also be broken into calcium oxide and carbon dioxide, and this calcium oxide combines with the silica present in the ore, because all silica has not been removed from the ore early, partly it has been removed, but there is some left out silica. It combines, this calcium oxide combines with silica, calcium silicate is formed, it is called slag, it is called slag, and this iron 2 oxide which is formed at this stage will be again reduced by CO or carbon monoxide to metallic iron, and lot of carbon dioxide will be produced, and this all will basically go as a exhaust gas. This all will go as a exhaust gas. So, overall you will get iron. Why we call this blast furnace? This blast furnace name is used because hot air is blown into this furnace and molten iron is here, and below is the slag. So, slag is separated out from the molten iron. So, from the blast furnace the iron which we call is called pig iron, because when the molten iron comes out from the furnace, its shape is like that of a pig, that is why it is called pig iron. There is no scientific meaning to represent this pig iron, but pig iron means this has impurities of sulfur, phosphorus, silicon, manganese and about 4% impurity of carbon, because carbon is very much used. So, some carbon is will be there in this pig iron, but the term pig is just derived because of its shape. Now, this pig iron cannot be directly used for any purpose. So, it is converted into cast iron. What is cast iron? In cast iron the percentage of carbon is reduced. How we do it? We melt the pig iron with scraps of iron and coke using hot air blast again in a reverberatory furnace. So, hematite is there, scrap iron is there, or we can use coke also we use. So, result is that the percentage of carbon in the pig iron is reduced, and the resulting product is called cast iron. This cast iron is very hard and brittle. What we use finally is the wrought iron or malleable iron. This is the purest form of commercial iron. It is prepared from the cast iron by oxidizing impurities in a reverberatory furnace. What are the impurities? Sulfur was there, phosphorus was there. So, they will all be converted in the reverberatory furnace which is lined with hematite. Hematite oxidizes carbon to carbon monoxide like this. Now, here also limestone is added as a flux. What limestone does? It removes small amount of silica which is left, sulfur, silicon, phosphorus, they are all oxidized and passed into slag. Silicon which is present cannot be converted into a gas, it will be converted into an oxide silica. So, limestone is required. Similarly, phosphorus cannot be converted into a gas, gaseous product by oxygen. So, phosphorus will be converted into phosphate and limestone will take away this phosphate in the form of calcium phosphate. So, to remove the impurities of silicon and phosphorus, this limestone is added here, and if by the way any small amount of silica is coming as an impurity because of imperfection in the process, that is also removed. Sulphur will be oxidized and it will be passed into the slag. They will be passed into the slag, sulphur will be oxidized, it will be oxidized into what? Sulphur dioxide. So, the carbon which is left in the cast iron will be converted into carbon monoxide and sulphur into sulphur dioxide, and these two will go as a gaseous product, leaving behind the metal which is called wrought iron or malleable iron, and it is the purest form of commercial iron. This metal is removed and this metal is basically passed through rollers, and when it passes through rollers, the slag is separated out. Slag is of lower density and it is separate out. So, this is how we get iron from its ore. Now, let us learn more examples of extraction of metal from ore. First example other than iron we are going to discuss is of extraction of copper from cuprous oxide or copper monoxide. If you look at the Allingham diagram which we have discussed earlier also, you can see that the copper is on the top of this diagram. It is much above than the carbon and carbon monoxide graphs. This suggests that copper oxide can be easily reduced with the help of carbon or carbon monoxide or coke in the temperature region 500 to 600 Kelvin. So, copper is reduced by directly heating its oxide with coke. Most of the ores of the copper are sulphide ores, some of them contain iron. So, obviously, this problem of iron and the presence of sulphur in the ores has to be tackled, because the sulphides or in presence of iron we cannot directly heat the copper ore with the coke to obtain pure copper. If the ore is a sulphide ore, we have to roast it as discussed earlier or smelt it and get oxide. Then oxide can be converted into copper metal. So, actual process of the extraction of copper from ore is based on the fact that iron is present and copper is present in the form of copper sulphide and iron is present. So, to in the form of iron is present in the form of iron sulphide, it is present in the form of iron oxide. So, we have to handle iron in two steps. In one step we will handle iron oxide, in the second step we will handle iron sulphide. So, what is done to handle iron oxide is ore is mixed with silica and heated in a reverberatory furnace, which you have learnt earlier, and just to remind you, I show you the diagram of reverberatory furnace. This is the diagram of reverberatory furnace. Here the ore and mixed with the other material is heated, and the heating is carried out by the hot gases, and here all the conversions occur inside the furnace, and the impurities etcetera, they are removed in the form of slag. So, in this furnace, when iron oxide is heated in presence of silica, FeSiO3 iron silicate is formed, and it is called slag because it is not very useful material, and this is removed. Now, what is remained is copper sulphide, iron sulphide. So, here the material which we get out of the removal of iron as a iron silicate, we call it copper matte, and this copper matte contains mainly copper sulphide and iron sulphide. This copper matte is charged with silica. Why we add silica? It is because we are left with some iron in the form of sulphide, and then we blast the mixture in a hot air. The idea of using hot air is to convert the leftover iron sulphide into iron oxide, which again combines with silica to form iron silicate. And the second purpose of this hot air blast is that copper sulphide which is present is also converted into copper oxide. Now, this copper oxide which is formed converts or reacts with sulphide to get copper in pure form. This is called self reduction. This is called self reduction, and since sulfur dioxide just evolves from the copper. So, on the surface of the copper blisters are formed. They are just like if our skin burns, then the blisters are formed. So, similar to those blisters on copper surface blisters are formed, and this has led us to give the name of blister copper to the copper obtained in this process. The another example of extraction of a metal is that of zinc, and its extraction we will discuss is from zinc oxide. Zinc oxide can be directly reduced with coke or carbon monoxide, but it is not as easy as in case of copper. Why it is so that it is not as easy as in case of copper? If you again look the Allingham diagram, you will see that copper is on the top, but zinc is much below. The line of coke, oxidation of coke or carbon monoxide, they are below the line of zinc oxide after a temperature of 800 degree centigrade only. Below that they are not below the line of zinc oxide. This implies that coke or carbon monoxide, they can be used for reducing zincite to zinc provided the temperature is above this crossing point, and as a result we use a temperature of the order of 1673 degree Kelvin for reduction of zincite or zinc oxide. Now, the question is that how to have a homogeneous mixture. Homogeneous mixture of zinc oxide and carbon. For that purpose, some clay is mixed along with coke and this oxide, and the bricks are made. These bricks are then heated in a furnace at a temperature of 1673 Kelvin, and the zinc oxide is converted into zinc, and another product, carbon monoxide, is liberated. Now, the zinc has a low boiling point, so zinc can be distilled off, and by sudden cooling, which we call as rapid chilling, the zinc metal can be obtained. So, this procedure of extraction of zinc from zincite can be extended to other zinc ores. Other zinc ores are calamine, which is a carbonate, zinc blendy, which is a zinc sulphide. So, obviously, depending upon the nature of these ores, we have to apply a dressing procedure. Dressing procedure in metal extraction is the one in which you bring the metal from any form into an oxide form. Metal ore is brought into oxide form, because oxide form can be reduced only. So, this process of converting ore into oxide form is called dressing, and the dressing of zinc carbonate or calamine or zinc blendy or zinc sulphide are not going to be identical, because chemically these two ores differ. Zinc carbonate can be converted into zinc oxide or zincite by calcination process, whereas for zinc blendy, to convert it into zinc oxide, we will have to use the roasting process. And once these ores calamine or zinc blendy, they are converted into zinc oxide, the same procedure can be used for extracting zinc from the zinc oxide. A very interesting anomaly I would like to point out, that on the basis of Ellingham diagram, on the basis of free energy, it is possible to predict that a particular reduction will occur or not, but that particular reduction happens or not, that is the question we have decide only by doing experiment. Take for example, chromium oxide Cr2O3. If you look at the Ellingham diagram, if you look at the thermodynamic parameter delta G0, it is negative. It is negative for what? Its reaction with aluminum. So, what does it says? If the delta G value is negative and the value magnitude is so high, then it says that it is feasible at room temperature. So, what should happen? You mix chromium oxide with aluminum and you should get pure chromium, and aluminum should be converted into aluminum oxide, but this does not happen. So, the question is why? Why this does not happen when it is predicted on the basis of the parameter delta G0 as well as on the basis of Ellingham diagram? We can explain this anomaly if you look this relationship between delta G naught and equilibrium constant. For happening the reaction which has negative delta G 0, it is must that a equilibrium is set up. Now, if you look at the reaction, this reaction at the top, you will see that all are in solid state. So, if the all reactants and products are in solid state, they are at room temperature. So, there is no possibility that there will be an equilibrium, and since there is no equilibrium between the reactants and the products, so reaction does not proceed at all at room temperature. But what will happen if we raise the temperature? If we raise the temperature, then at higher temperature the delta S will become positive. If you recall the equation delta G is equal to delta H minus T delta S, then temperature is high, delta is positive. So, this term is negative, and this term can even overcome for an endothermic reaction and can make overall delta G negative. And this happens in this case also, that increase in temperature makes the value of delta G more and more negative. So, now obviously the equilibrium established because there is one phase solid and another phase liquid. In this situation the equilibrium is set up and reaction becomes feasible as temperature is increased. So, the reduction of chromium oxide with aluminum occurs at higher temperatures, not at room temperature, but at high temperature than the room temperature. Thank you very much.